All right, in this next lesson, we're going to look at Newton's Laws 2, and in this lesson, we're going to look primarily at Newton's laws in accelerating systems. That's going to be what we're going to look at. You know, last time we talked about statics, cases where the system was not accelerating, and here we're going to look at cases where they are accelerating. So, Newton's second law states that the net force on an object is equal to its mass times acceleration, where the net force is the total force. That is, we sum up every force on it in all directions. That'll equal the mass of the object times its acceleration as a vector. So previously we talked about statics. We discussed how to solve solutions or situations where the acceleration is zero and therefore the net force is zero. But let's talk about what happens if this acceleration is not zero. So it's a non-zero case. If we do that, then we can solve the system we're looking at by summing the forces on the object. That gives us our net force right there, and then setting those equal to the mass times acceleration in both the x direction and in the y direction. Because these are vectors, when we set this up, we're really going to set up two equations. We're almost going to have an F net, x equals the mass times the x acceleration, and then we're going to have an F net y, the sum of all the components in the y direction, is equal to the mass times the acceleration in the y direction. Now, the way we're going to typically do this is by basically situating the problem so one of these accelerations, either x or y, ends up being zero. Because if it's true that we can get the direct acceleration in the x direction to be zero, then it means that the net force in the x direction, the forces are simply equal to each other. We can sort of cancel them out. It turns into a statics problem. We do the same thing if we manage to get a y to equal zero. And so if we have an acceleration, this is sort of our third point down here, if the acceleration is not along the x or y axis to start with, say that we've got a ball that's accelerating up in this direction right here, is that what we would want to do is we'd want to rotate the coordinate system so that the acceleration does point along an axis. And so let's say that this particular ball, my screen's not working all of a sudden. Let's see. So let's suppose that we basically have a case where the angle this ball is, we'll say, is going to be 20 degrees, right up there. And so what we'd want to do is we'd either want to rotate this coordinate system in this direction by 20 degrees so that now that the ball's acceleration is pointing in the x direction, or we'd want to rotate it upward, this case by, I guess it'd be 90 minus 20, 70 degrees. So that the ball's acceleration is going upward. Because if we do that, then whenever we set this up, is that in, say, the case that we have over here is that we know that the y acceleration is equal to a, but the x acceleration is equal to 0. In the case of this one right over here, the x acceleration is equal to a, but the y acceleration is equal to 0. It's just going to let us solve these problems a little bit more easily. You don't necessarily have to do it this way, but it is going to make your life a lot easier if you do so. So you want to first rotate the coordinate system so the acceleration points along an axis, and then doing this, as in the last point, ensures the net force along one axis is 0, while the net force along the other axis is your total mass times the total acceleration, just our F net equals ma. And so let's take a look at how we might apply this. So let's say three men are pulling a 150 kilogram piano across a frictionless surface. The first man has a force of 200 newtons due south, the second man 250 newtons at 160 degrees, and the third 180 newtons at 210. What's the acceleration on the piano? And so we're looking down from the top on this particular piano right here. Here's our piano. Let's say it's an upright right there. There's our piano. All right, so what we know here is that we have three men who are pulling on this piano, or pushing on the piano, or pulling, I guess. One is going to pull straight down right here with a force of 200 newtons. Our second man that's on here is pulling 250 newtons at 160 degrees. So I'm going to exaggerate a little bit here. 160 degrees would be off from negative 180 by 20 degrees, obviously exaggerating. And so that's at a force of 250 newtons right here. And then our third man who's doing this is at 180 newtons at 210 degrees. So 180 is due south, so 210 degrees would be 30 degrees on the other side. And so this angle in here would be 30 degrees, and he's pulling with a force of 180 newtons. 180 newtons right there. All right, so this is our situation, and the question is, what is the acceleration of the piano? So to work this out, we don't have to worry about rotating the coordinate system because of the fact we really don't know which way to rotate it here. We just want to find what the acceleration is. And so to do that, we want to look for the acceleration in the x direction and in the y direction. And so let's say we're going to start off looking for this, let's say in the x direction. And so to look for this, in the x direction, basically what we're going to look at is we're going to look at the forces in the x direction. And so the forces in the x direction, we're going to break these things into components. So for our first vector, the 200 newtons due south, that has no component in the x direction. And so we don't really have to worry about that one. For our second vector, 250 at 160 degrees, if we broke this into components, one component going this way, one going this way. For this one right here, we have two components, one like this, one like this. Really sort of setting this up is that we would say if the 20 degrees is our angle in the 250, that means this interior angle right here is 90 minus 20, 70 degrees, right there. This angle that's inside here that you really can't see very well, I'll draw a little arrow down there, would be 90 minus 30 is 60. That's running off the edge of my screen, 60 degrees, right there. So 60 degrees is our angle right in there. So for our x direction, we have two vectors that point in the x direction. The 200, as we said, goes due south, has no x component. For the 250, it would have to be 250 times cosine of 70. And so we'd say 250 cosine of 70 degrees would be the one that's in the positive x direction. We know that if we're going to have to subtract off from that the one that's in the the one that's the 180 in the x direction, the other vector that has an x component, since it's moving in the negative direction, moving over that way. And so that's going to be 180 times the cosine of its angle, which is 60 degrees. And we do this, this is going to be our net force in the x direction. Those are the only forces we have in the x direction. It's going to equal to the mass of the object times its acceleration in the x direction. Really, it's a component of the acceleration right here. And so if we want to continue setting this up for x, we would say, all right, let's solve this out here. 250 cosine 70. If you put it in your calculator, you should get 85.505 newtons minus our next part right here, which is 180 cosine 60. Cosine of 60 is just 1/2, and so that should be 90, equals the mass of this piano, 150 kilograms, times AX, right there. All right. If we go ahead, we can solve for AX here just because we're going to run out of space unless we do this. If you solve this out, solve for AX, you should get that the X component of A turns out to be 0.029966 right there. And so that's it for X. In the Y direction, it's our next case we want to look at. We have three forces in the Y direction. In this case, they're all pointing downward. They're all negative. The first one is our 200 newtons. That's just pointing straight negative, and so negative 200 newtons minus our next one, which is going to be the 250 over here. Its component is going to be 250 times the sine of 70 degrees. And then minus our last component, which is the 180, the third man, 180 times the sine of 60 degrees. These summed up should be our net force in the Y direction. And so that's going to equal the mass, which we said was 150 for the piano, times the acceleration in the Y direction. And so in setting this up, we can once again do the math here. If you do the math, then you should end up getting that the acceleration in the Y direction, just solving for that, is, let's see, I've got it down here, negative 3.938 meters per second squared should be our unit here. Same thing is true up here, meters per second squared. All right. So we now have the acceleration's components in the x and in the y direction. And so if we were to sketch this out, we would say, all right, it has a component in the y direction of negative 3.938. It has a component in the x direction, is very, very small, of 0.029966. And so we want to find the hypotenuse, which is our total acceleration. So to do that, we're just going to use Pythagorean theorem on this. And so using Pythagorean theorem, we say that the acceleration we have here squared is equal to the x acceleration 0.029966 squared plus 3.938. Notice that we don't have to worry about the negatives on these because of the fact that they're going to square. So the negatives are going to go away. We solve this. We should get an acceleration, solving this out, of right at 3.938. The reason why is because the fact that this component we have right here of the x is so very small, it really doesn't end up making much of a difference at all in terms of overall magnitude. So meters per second squared. If we want to find the angle on this, because the acceleration is a vector, then we would also need to basically set up our triangle up here. Over here, we're going to say we've got an adjacent. If we're looking for this angle right in here, we've got an adjacent, we've got an opposite. That's going to be tangent. And so we would basically say that the tangent of our angle, call it theta, is going to be equal to opposite 0.029966 over adjacent 3.938. And so when we do that, solve for theta, I get theta to end up being 0.43 degrees. It's a 43 degrees right there. Very, very small value for theta. And so looking at my final overall answer, I ended up with 3.938 meters per second. It's the acceleration. Significant figures, we have 2 right up here, 2 here, 1 right there, so it's going to knock it down to 1. So 3.938 would round to 4 meters per second squared at an angle. In this case, it's a 0.43. It is pointing off just barely to the left, so it's just beyond 180, and so this should be at an angle of 180 point round to 1 decimal place, 0.4 degrees. And so my final answer is that this object will have an acceleration of 4 meters per second at 180.4 degrees. So this would be one application of a case where we have acceleration. So let's take a look at another problem. A 50 kilogram box is pushed up a 25 degree frictionless inclined plane. What force must be applied to the box to have it accelerate up the plane at half a meter per second, 0.5. So we have a 25 degree frictionless plane right here. Here's our angle right here is 25 degrees. We have some box on this plane right here. We know that there is a force applied up the plane. Let's say what force? Normally I would probably say, and I forgot to say it in here, say the direction of the force. What force up the plank, or what's the minimum force? In this case, this force, the minimum force would be up the plank. We're going to call that our applied force. We also have forces of gravity pointing down, and we have a normal force, which is getting cut off here, pointing in this direction. Normally what we want to do is it says it's going to cause it to accelerate up the plane at an acceleration of 0.5. And so since the acceleration is pointed up at an angle, we want to rotate the system so the acceleration is pointing along one direction. Easiest way to do this is to take this system and rotate it by 25 degrees. And so now if we rotate this by 25 degrees, here's our box. It now has a normal force which points upward, an applied force which points due east, if you think about it that way. There's our normal force, there's our applied force, and the gravitational force is now going to be angled over here. And so really we can start thinking about this gravitational force in terms of its components. It's going to have an FG y, and it's going to have an FGX. This interior angle in here is how much it's rotated, and so 25 degrees. You can read that in there. All right, so this is sort of our setup here. So what force must be applied to the box to have it accelerate up the plane at 0.5 meters per second? Now that we've rotated it, this 0.5 meters per second is the acceleration in the x direction. It's our total acceleration, but given the way we've rotated, it's also in the x direction. That's useful, because if we can just look at the x side of things, we may be able to solve it without having to look at y at all. So let's look at our forces in the x direction. We're going to call to the right positive because that's the direction of the acceleration here. And so our force in the right direction is Fa, our applied force. From that, we are going to subtract the x component of the gravitational force. Well, what is that? Well, it's normally going to be Fg, the gravitational force. Since we're looking at the opposite side of this, it'll be sine of our angle, 25 degrees, would equal the mass of the object, which is 50 kilograms, times the acceleration, which in this case, actually, I guess I left that off here, is going to be 0.5, make that a 0, 0.5 meters per second squared. All right, so looking at what we've got here, the only thing we really need to get is our force of gravity. Well, that's pretty easy to find here because we know that the force of gravity on an object is going to be equal to its mass times the acceleration due to gravity, which is 9.8. And so 9.8 times the mass, 50, right here, do that math, you should get about 490. And so rewriting this guy right here, the Fa minus 490 sine of 25 is going to equal to 50 times 0.5, which is just 25 right over there. And so we should be able to go ahead and solve through this pretty quickly here. Whenever you do this, we get FA minus 490 sine 25. Put it in your calculator, you'll get 207.083 equals 25. And so solving for the applied force, in this case by adding 207.83 on both sides, we get the applied force has to be 232.083 newtons. Has to be our applied force to give it this box an acceleration of 0.5 meters per second. Since our significant figures here, this has 1. The angle doesn't really matter for here. This has 1. Our answer is going to have 1 sig fig. And so we'll round to 1 sig fig here. And so our final answer would be 200 newtons is the force on the box. Okay, so that would be another way that we would use Newton's second law to solve a case of accelerations. So let's see one other case, a little more complex case here. Here we have a box sitting on a plane, just on the edge of a table. It has a rope attached to it, or string attached to it, which is attached to some other mass which is dangling over the edge. We have a pulley, so we don't have to worry about any type of friction that's going on. This is a frictionless plane as well. I didn't say it in the problem, but I should have. So frictionless plane also here. Nothing going to be opposing this box moving in the leftward direction as it gets pulled off by the one that's hanging off the side. And so we have a 5 kilogram box tied to a box of unknown mass dangling over an edge. What is the mass of the dangling box if the pair accelerated 1.5 meters per second squared? Sort of common sense says that the heavier box X is, the faster the acceleration should be, the higher value of the acceleration we should have here. And so we want to find out what is it. So to do this problem, we have to figure out all the forces on here. And so if we sketch out the forces, we say, all right, on this 5 kilogram box, there is a gravitational force, Fg downward. There is a normal force, Fn upward. There is going to be a tension force pulling along on this 5 kilogram box. On box X, there is a gravitational force, Fg over here. There is a tension force pulling upward here. Now, the first thing to look at here is the fact that Newton's second law talks only about external forces. Of this whole system, these two boxes tied together, they're not going to separate, they're not going to come apart. This is one whole system, the 5 and the X put together. And so with the 5 and the X put together, these two tension forces right here are internal forces. They're things that are pulling on the boxes from inside the system. And so as a result, if we are basically looking at the system as a whole, the whole kit and caboodle, the 5 and the X, we can ignore the tension forces. It's not that they're not there, it's simply that since they're internal, they cancel each other out. These are going to be the same value, these tension forces, because the wire here is going to have the same tension for both of them setting up here. So in this case, we don't have to worry about them. Now, what we do want to do is we do want to say this pulley that's sort of in the middle here is redirecting the forces. The box X, the gravity for box X as it sort of pulls downward, is pulling the 5 kilogram box to the left. And so something that makes sense to do is to straighten out the system. Basically, take our box X and we're going to rotate it up by 90 degrees. And so sort of my little green line right here is our rotated version here. And so with this box X, the gravitational force is pulling in that direction. I'm sort of getting into the problem here as I'm doing it. But this sort of simplifies things out a little bit, because now instead of having a case where you're like, okay, that gravitational force on box X pulls down, but though it's going down, it's pulling the 5 kilogram blocks to the left. Now it's all pulling to the left. Is gravity actually pushing to the left? No, of course not. Not on that box X. But we can treat it like it is for the purposes of solving the problem. So, if this is true, then we basically have 3 forces on this system. We have the normal force, which is pushing the 5 kilogram box up. We have the gravitational force, which is pulling it down. And we have a box on the box 5 that's pulling it down. And we have the gravitational force on box X, which is pulling it to the left. And I say left in sort of air quotes that you couldn't see right there. So those are our 3 forces on here. Now we're told the box accelerates at 1.5 meters per second squared. Now the question is, which way does it accelerate? And common sense should tell you that that 5 kilogram box is not accelerating upward or downward. It's sliding along the plane. And this box X is not accelerating rightward or leftward. It's accelerating downward, which in our new rotated version is to the left. And so everything here should be moving off to the left. And so this acceleration of 1.5 meters per second should be moving to the leftward direction. And if it's moving in the leftward direction, then all we care about is X. The Y's have to cancel. The normal force on the 5 kilogram box and the gravitational force on the 5 kilogram box both have to add up to be 0. And so let's look at the X direction forces. Our X direction forces are the gravitational force on box X. And so we're looking at the gravitational force on box X would have to equal the mass times the acceleration. And so let's find what the box force of gravity on box X is. Well, we said before, the force of gravity on an object is its mass times 9.8, the acceleration to gravity, assuming it's on Earth. And so for that, our force on X is going to basically be 9.8 times its mass, which is, we're calling X in this point, would equal the mass times acceleration. Now, here's where we have to be a little careful, because what object's accelerating? Is it just X, or is it X and the 5? This force that the FGX is putting here that pulls down on box X is also pulling on the 5 in the leftward direction. It's pulling on the whole system, not just of X, not just of 5, but of 5 plus X, the whole thing. And so as a result, when we talk about this mass right here, you're not just going to use the mass of an individual piece unless you're adding up all the forces on an individual piece. If this mass right here is going to be on X, then the forces, we have to include that tension force that we got rid of. But if we're talking about everything, both X and the 5 kilogram box right here, then we're going to use the total mass, which is X plus 5 times the acceleration, which we already were told in the problem is 1.5. Now we have two values of X in the same problem. We should be able to solve for X. So 9.8X is going to equal to 1.5X plus 5 times 1.5, which is 7.5. Right there, we're going to subtract off 1.5x from both sides. 8.3x is going to equal to 7.5. Divide both sides by 8.3. And so we should get x, if you do the math on that, have a mass of 0.9036. 0.9036 kilograms. Significant figure-wise, that's 1 sig fig right there, 2 right there. So our final answer should have 1. And so our box has a mass of 0.9 kilograms, box X. And so if box X has a mass of 0.9 kilograms, then the 5 kilogram box on this frictionless plane attached to it should accelerate, and box X, they're traveling together with the acceleration, with the acceleration of 1.5 meters per second squared.